Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, is welcoming you all to a new amazing video in which we are gonna talk about a crazy thing. I would say this is the what we are gonna talk about in this video. I was like playing around with the Gaussian integral and I just reached up there. I would like to show you that, don't worry. So before that, let's talk about the Gaussian integral. And you know what? I have recently uploaded the proof of the Gaussian integral. I hope you have watched that proof, the Gaussian integral. Basically, it is the integral from negative infinity to infinity of e to the negative x squared dx is the square root of pi. And we have talked about this integral and its result in that video. Although I will just paste the link of that video in the description box of this video, don't worry. And basically, or we can say integral from 0 to infinity of e to the negative x squared dx is the square root of pi over 2. So now you would say, Aman, what we are gonna do with this? I would say, if you're a real mathematics student, like higher mathematics, so after looking at this integrand, you would think of something. Well, we have studied about this thing. This is the Taylor expansion or series. And we know that it's e to the z equals the sum as n goes from 0 to infinity of z to the n over n factorial. Okay, now you would consider, like you would think that what Aman is really talking about. Like if we talk about this integrand, it is e to the negative x squared. So basically we just have to replace this z with negative x squared here in order to get the integrand in terms of an infinite series. So if we talk about e to the negative x squared, so it is the sum as n goes from 0 to infinity of negative 1 to the n and it's x to the 2n over n factorial. Oh my goodness. You know what? First day I saw this integral, I literally didn't know about the Taylor expansion or whatever it is. But when I think about this, when I learn about this, I was like, can we replace this with an infinite series here? And the answer is yes, let's do this. Why? Why we cannot do that? Well, we are wanderer, we are explorers, so let's just explore around here. So basically, I would represent the Gaussian integral with g. So it's g equals integral from 0 to infinity of e to the negative x squared dx, although it evaluates to square root of pi over 2. But if we talk about g, so it's integral from 0 to infinity, the sum as n goes from 0 to infinity, and it's negative 1 to the n over n factorial x to the 2n dx. And well, due to linearity, we can say the sum as n goes from 0 to infinity and negative 1 to the n over n factorial is independent of x. So times the integral from 0 to infinity of x to the 2n dx. Okay, now you would say, Aman, why we cannot express this integrand in terms of this infinite series? Because of this integral comes out, this integral incarnate here, and this is not a proper integral at all. So to make that a proper integral, I would use limits, right? So basically, this video is really short. So g can also be written as a limit as z tends to infinity. Let's say z. So it's this sum as n goes from 0 to z, because z is tending to infinity, right? and this negative 1 to the n over n factorial, an integral from 0 to z of x to n dx. And if you try to evaluate that integral, so that integral is going to be evaluated to limit z tends to infinity, the sum as n goes from 0 to z of negative 1 to the n over n factorial, and it's z to the 2n plus 1 over 2n plus 1. So finally we can say g comes out to be limit as, z tends to infinity, the sum, z as n goes from 0 to z of, negative 1 to the n over n factorial times 2n plus 1, and it's z to the 2n plus 1. And what was the result that we have found here for z? So finally we can say that limit, so it's limit as z tends to infinity, sum as n goes from 0 to z of negative 1 to the n over n factorial times 2n plus 1, and z to the 2n plus 1 was the square root of pi over 2. Basically why I did that thing, because look, everything is fine, like we can replace this z with infinity, so it's an infinite series, right? But if we replace this z with infinity, so it doesn't make any sense, right? But this limit has a closed form, and that is the square root of pi over 2. So basically we can say that this sum as n goes from 0 to infinity of negative 1 to the n over n factorial times 2n plus 1, and it's infinity to the 2n plus 1, comes out to be the square root of pi over 2. Like, take a look at this thing. So basically we have this, we vanish all these things. So infinity to 2n plus 1 as n goes from 0 to infinity as well. So it comes out to be the square root of pi over 2. I think I am wrong because it doesn't make any sense. And please guys, if I'm wrong, because I'm not sure about that, if I'm wrong at any point, please, I'm just giving you this responsibility to just tell me where I'm wrong, because I don't believe even on my solution or even on this part. This is mind-blowing. Like, this is mind-blowing in the sense that it's not good. It's mind explosion, I would say, rather than mind-blowing. So that is why I was just keeping the recent uploaded video, that is the Gaussian integral video, as a prerequisite video for this video. That was so this was the prerequisite, I would say, because my channel's philosophy is like, Aman, if you are teaching something, prove it down. Although I haven't proved the Taylor expansion of e to the z yet, but yeah, I'll prove that down as well. Don't worry about that. So yeah guys, seriously, I'm disturbed by this result, and I would like you to just help me out why I'm doing this and why I cannot do that. Is there any kind of restriction that I'm not following so far? So yeah, again guys, if you got to learn something from this video, maybe you are gonna just criticize me because Aman, you cannot do this, but it's all right. So please make sure to like, subscribe and share. And if you have any kind of doubt so far, I think it's full of doubts. Okay, so you just have to ask me. I'll try to answer them as fast as possible. And stay tuned for the next video guys. Again, there are a lot of things which are being to be discussed. Goodbye guys, take care, love you, and come up for the next video, I would request you.